In this video, I will demonstrate how to construct and analyze a Bland-Altman plot. Bland-Altman plots are typically used to analyze the agreement between two different types of measurements, usually in a continuous or quantitative variable. Now, this is similar to what we do with interclass correlation, but the reason we use Bland-Altman is very often we can have two sets of data that can have a good correlation, which may indicate that they have similar variance in their measurements, but that could just be a sign that one has chosen a fairly widespread sample, and so a high correlation does not automatically imply that there is good agreement between the two methods. So Bland-Altman is an alternate way to try and address the difference between two sets of measurements and whether that difference is large enough to say that it's systematic and that these two types of measurements do not agree very well and therefore do not measure the same. So because of that, Bland-Altman plots are typically used to compare two clinical measurements that each have the potential for some error in their measure. So what Bland-Altman plots allow us to do is investigate the existence of any systematic difference between the measurements and to identify possible outliers. So what we do is we determine the mean difference between the two sets of measurements, and again, this would be people being measured twice using two different measurement techniques. And in this example, we have two different measurements of body fat percentage. So we have 25 subjects were measured using two different techniques that were intended to measure body fat percentage, and we're going to see how well these two measurements agree. So what we're going to do is determine the mean difference as well as the standard deviation of these differences, and this is going to help us measure random fluctuations around the mean difference. So if the mean value of the difference is significantly different from zero, in other words, zero would be perfect agreement, then that indicates the presence of some fixed bias. And if there is a consistent bias, it can be adjusted for and determined by subtracting the mean difference from the new method. So it's one of the methods. So it's common to compute 95% limits of agreement, which we're going to talk about how to do, and then look at how far apart these two measurements were. And we can also use regression analysis to determine whether or not we have any significant bias. So let's go ahead and go through an example here of how we would do this. So as I mentioned before, we have two variables here. We have body fat percentage measured using one type of measurement, and then body fat percentage measured using a different type of measure. And so we want to see how well these two measures agree with one another. Now, the first thing we need to do, and unfortunately SPSS does not have a drop-down menu for Bland-Altman, so we're going to have to use some of SPSS's features independently to perform this technique. So the first thing we need to do is come up with the difference between the two measurements. And so what I did here is just went to transform compute and just created a new variable, and I'll show you what I did here. Is create a new variable where I took body fat 1 minus body fat 2, and that was my new variable of the difference. Now we also need to construct a mean of the two measurements, and I also did that by creating a new variable, and I'll show you what that one looks like. So I created this new variable called mmean. So I took body fat 1 plus body fat 2, added them, divided by 2 to get a mean of those two measurements. And so that's some of the data that I'm going to work with. So the first step we need to do is determine if there is a significant difference between the two measurements. And in other words, is there a difference or is there a variation from zero of the difference between the two measurements? If the difference of the two measurements varies significantly from zero, then we can say that these two measurements don't agree. So we need to assess that null hypothesis first. So how we're going to do that is by doing a one sample t-test. So we're going to go to compare means, one sample t-test, and our test variable is going to be the difference score, DIF, and our test value will have to be set at 0, because again our null hypothesis is that there will be zero difference between the two measurements. In other words, they will completely agree. So we're going to test that hypothesis using this. So we move difference to the test variables box, make sure test value is set at 0, and then we click OK. So there's a couple pieces of information we're going to need from this. First of all, we're going to need to know the mean difference as well as the standard deviation of the difference. And I'll explain why in a little bit, but you'll need to track that. And then we can look at the results of the t-test. And we can see here that there was not a significant difference between 0 and the mean difference of our measurements. So this is to say that there is not a statistically significant difference between our two measurements. So that's good news. That means that there is a certain level of agreement between these two measurements. Now, if this was significant, then we would say we wouldn't really have to go any further, and we could say that these two measurements are significantly different from one another, so obviously they cannot show a useful level of agreement. Okay, so that's our first step. Now our next step is to construct a basic scatter plot, and we're going to use the graphing procedure to do that, and that's going to help us visualize these data points relative to what we would expect to be a normal variance, and this is where the idea of the BlandAltman plot comes from. So we're going to go to the graph menu, go to legacy dialogues, and choose scatter plot. Okay, we're going to choose a simple scatter and click define. Now in the y-axis we want to put the difference score that we calculated, and then in the x-axis we want to put the mean of each of those pairs of measurements. So we put the difference score on the y-axis, the mean of the scores in the x-axis, and then we go ahead and click OK. And then here is our scatter plot. So again, we've got our mean along the x-axis and our difference between each set of scores here on the y-axis. So our next step is to go ahead and put in the mean difference horizontal line, and then the upper and lower confidence limit lines, so we can get a sense of how well the data fits kind of that normal expectation of agreement. So in order to do that, we want to double click on our graph to get into the chart editor. Now, as I mentioned, we're going to add 3 lines. So the first line we want to add is the mean of the difference, which, as we had seen earlier, was minus 0.56. We want to add that line first. So we're going to go to the options menu and choose y-axis reference line. And so in the position box, we want to put the mean difference score that we found. And so in our case, we found a minus 0.56. So we enter that into the position box, we click apply, and then close. And so there's our mean difference box. So we can see that most of the data points are clustered around that box. Now our next step is to determine our confidence limits and then put lines in associated with those. And so in order to do that, we need to know the standard deviation of the difference. We're going to take that standard deviation of the difference, multiply it by 1.96, and then we're going to add it to the mean difference. So that's going to be our upper limit score. So we're going to take minus 0.56, add it to the product of 1.96 times 2.1, and that gives us a value of 3.556. So that's going to be our upper confidence limit boundary. So now we want to add that line. So we go back to the options menu, click y-axis reference line, and now we enter in the value that we want, which, as I mentioned, is 3.556 positive. Click apply, and then click close, and there's our upper reference line. Okay, now we want to add our bottom reference line, our lower confidence limit. So in this case, we again take that product of 1.96 and 2.1, and we're going to subtract that from our mean difference, in this case minus 0.56. So we take minus 0.56 minus the product of 1.96 and 2.1, which is 4.116, and that gives us a value of minus 4.676. So now we want to go back to the options menu, the y-axis reference line, and enter in that third reference line. So minus 4.676. Click apply, and then click close. And there is our BlandAltman plot. And so again, this middle line indicates the mean difference between the two measurements, and the upper and lower lines indicate the 95% confidence limits for these measures. Okay, so there's our BlandAltman plot. Now, as we begin to interpret the BlandAltman plot, one of the first things we start to look for is if there's a trend between points being above versus below our mean difference. So there is proportional bias if we're seeing a trend with a greater number of data points being above the mean difference line versus below the mean difference line. So a simple test to determine a linear trend of this type would be now to run a linear regression procedure. So now we want to go to the Analyze menu, go to Regression and Linear, okay, and place the difference score in the dependent box. So that's our difference variable in the dependent box. And then M mean in the independent box. And then click OK. And then the default information that we're given is appropriate. So now in order to interpret this, we go down to the coefficients table here in this output. And so what we're given, along with a model coefficient for the M-mean variable, we have a t-value and a significance level for the test of the hypothesis that the coefficient for M-mean equals 0, which is what we want to see. We want it to be as close to 0 as possible. So if we reject the null hypothesis that M-mean equals 0, then that's consistent with the presence of proportional bias. If we accept the null hypothesis and say the t-test is not significant, then that tells us there is no proportional bias and there appears to be a level of agreement. So as we look down to M-mean here, here's our coefficient for M-mean. Here's the t-value and the significance for that t-score. So as we can see here, we do not have a statistically significant t-score. So we accept the null hypothesis is that there is no proportional bias. So that, again, that is a good thing. That's giving us an indication of the level of agreement, that there is not a trend where there's more data points above or below the mean difference line than we would want to see. So there is no trend, there is no proportional. Now, BlandAltman recommend that if we do find proportional bias, in other words, that the variance of the difference varies across the range of n-mean. In other words, the vertical spread of scatter points is much narrower at low values than at high values of n-mean. Then they suggest that we calculate the natural logarithms of the two measures, A and B, body fat 1 and body fat 2 in this example. Recalculate the difference, and then the mean measures with these new variables, and then redraw our plot with these new values, and then reassess for agreement of these two measures. So hopefully, in summary, what we've done is we learned how to construct a BlandAltman plot to determine the level of agreement of two continuous data type measurement techniques. We constructed our BlandAltman plot, and then we talked about some various steps that we can go through to determine if there is a level of agreement or if there is proportional bias in the measurement. And so we used a one-sample t-test to do that. We used a visual inspection of the BlandAltman plot, and then we used linear regression to determine if there is proportional bias or if there does appear to be a certain level of agreement between these two measurements. So hopefully you learned something in this video, and good luck using this technique in your own research.